Okay. Hello and welcome everyone to this Digital Twins in Smart Manufacturing training day 1. So we will be starting with that subject. But first, a little bit about me. My name is Joonas Kortalainen and I work as a full-time lecturer / researcher in Satakunta University of Applied Sciences. Been working here for the past, I guess 10 years is now the time. If I think about 10 years about, or 11 or a bit more, not sure. But I started as a student working part-time, and then I developed there doing summer jobs in the school, working with machine vision mostly. And then a few years later, I got a glimpse on simulation, automation simulation, and started working with that, and then started teaching that. And then a few years back, like 1 to 2 years ago, started teaching 3D printing also, as I picked that up like 5 to 6 years ago, to when we first got our first 3D printer in the school. Teaching and working with simulations and 3D printing and machine vision projects is basically my duties. But that's about me. So what are the learning outcomes of this training? Well, first and the major thing is to understand the possibilities of a digital twin. The possibilities that you can gain from using a digital twin in the manufacturing process or any other industry. And the idea is also that you start thinking of the factory of tomorrow before you even invest a dime into it. So that you will start to think about ways that you could make use of simulation and digital twins in that point, in that case. And like in the third slide, it says gain the knowledge to identify the potential use cases for digital twin. We will get more detailed on the fact that what is a digital twin, obviously, but we will also check on the stages of a digital twin, because not everything is a true digital twin, even it says so. There's like still different stages of that. So those are the outcomes of the training. Content of the training, again, repeating the same old. We get to know what the digital twin is, how is it beneficial to the user, company, etc., and who uses it. We get a few case examples on that. I mean, no, just a few, because it's still so new. And we will on the first day, we will check on mostly on the theory, but in the last dots there that you see, we will go through like how it's done in its simplest form, like the simple level. How can you make a digital twin from virtual to physical, and how can you make a digital twin from physical to virtual? We will check those. And in the schedule, that is explained a bit more precisely. So today we will go through the theory part, just talking about digital twins in the manufacturing and etc. And then there will be the briefing for the assignment, number 1. We will have a short break in like 50 minutes, and then we will continue after that. And tomorrow will be the assignment day. And on Wednesday, we will go through examples of digital models and digital shadows and briefing for assignment 2. And as you can see, on the Wednesday, I don't mention digital twins. So those two things will be the other stages of a digital twin. So they are digital twins, but they are the different stage forms of it. We will go through some case examples that we have done and talk about those. And on the third day, on Friday, we will make our own digital model, digital shadow, or I will show how to make one on the go, so to say. And hopefully we will have one video also available that shows digital twin working. I can't promise that because it's not in my hands, but I will ask if it's possible to get it by Friday. So yeah, this is the schedule of the training. And then on the agenda of today, we will talk about first a bit about the industrial revolutions to get like a backstory for all of this. And then we will talk a little bit about smart manufacturing. And then it should say digital twin there, but it's missing. But it should be after the smart manufacturing part, and then the history part of the digital twin, and then the different theories of the digital twin, because there's like several theories on that too. It's really not a simple thing. And what is the digital twin in its stages, and where is it used, and how is it used, and how can you make one? So those will be on the list for today too. So let's jump on the first thing, the industrial revolutions. Because before we can talk even about the digital twins, we need to make the base for our topic. We need to take a bit of a step back to see the big picture of this industrial technology revolution that has been going on for the 200 to 300 years, to get a better picture and idea of it, to see the importance of it. Why is it a major thing? Brief glimpse on the whole picture of this whole idea, where the digital twin belong into, and that thing is the industrial revolution. So it's really part of it. But what does an industrial revolution mean? I mean, well, it basically means that the development of technology has surpassed a certain point, sort of industrialization of a certain areas, to diminish the human labor or ways to gain power, which helps the human power or fuel, so to say, which help the human worker in its process of doing the daily chores or the labor that the human does. So the first industrial revolution. In the picture, there's the biggest thing that came with the first industrial revolution, the steam engine. The first industrial revolution happened in the late 1700s and early 1800s. It started in the Great Britain, and it's spread from there all over the world. It started basically when people started to take notice about coal. They started to take notice about coal, oil, and natural gas, that you could get energy or heat from these materials. Coal ended up being obviously the most popular one because of its availability and the ease to get it, the easy way to get it at that time. because you just took a pickaxe and swung away, and you gained coal from that. And as people noticed that you could burn this black stone-like material, this coal, and gain heat or energy from it, they started to create mines, coal mines, to dig this material more. And so that they gained more of the material, they needed to go deeper in those mines. So they ended up going deeper, obviously. And as they went further down and down, the mine started to fill with water. And they needed a way to get the water out of these mines because the water was in the way of mining the coal again. So first they used horses that pulled buckets of water out of the mines, but that was way too slow. I mean, it worked for a point, to a certain point, but it ended up being way too slow process for its application. And then a gentleman called Thomas Newcomen started thinking about this, and he ended up designing a steam engine that could use coal as a fuel and create steam in the end. This steam will drive a piston with the help of a partial vacuum created, and this enabled the process of pumping the water out of the mines. So this was the first application for a steam engine to pump water out of the coal mines, because it proved out to be a lot faster, obviously, again, than proved out to be a faster method to get water out of the mines than with the horses. And as you, again, use coal as a fuel for this steam engine, you will obviously need more coal to pump again the water out of the mines. So it created basically a loop. So more coal was needed. We needed more mines and more steam engines and etc. And a few years passed, and then came James Watt, who developed the steam engine further to be able to so that the steam engine could be used in different application areas, for example, steam locomotives and steamboats and even cotton mills. So that started a process called mechanization. So this was the first industrial revolution, and the name for it was so-called mechanization. So creating equipment for human labor, for replacing human labor, human physical labor. Then came the second industrial revolution, Industry 2.0, and this happened in 1870 to 1940. With this revolution, there came a production of electricity, electric lights, electric engines, combustion engines, telephone, radio, automobile, and airplane. So quite big things came with this revolution, things that are still in use. I mean, the basic concept, of course, in different form. And so many of the major technologies that we have now, or the building blocks for them, came really from this era, or this revolution, so to say. And as the inventions of electricity needed a way to be created, came, for example, the help of the first industrial revolution in the inventions, the steam engine. So you could create electricity with a steam engine. And with the help of the electricity that came with this revolution and the electric engine, came the big thing that was major in this second industrial revolution. Not a thing, but an idea or a way to make things. So the key word in the second industrial revolution was mass production, and that was the big thing. So you could mass produce items. In the first revolution, we created equipment to produce stuff, but now we had the means to get more power, more efficient with these things, and we started to mass produce. Then came the Industry 3.0. And when we jump onto the Industrial Revolution number 3, called Industry 3.0, we have to take, again, the leap in time, and now we're in the 1960s. What this revolution brought with it was that it brought IT and computers to the table, microcontrollers, microchips, and etc., which then again gave us the possibility to automate things. So that was automation, or automate was the keyword of that industrial revolution, because now robots started to enter the manufacturing field, and because of this, the manufacturing process started to get obviously automated, because now robots will do the jobs of the humans, and this was a huge leap forward in the manufacturing, as machines started working more and the human could be put elsewhere to work with. So yeah, and in the picture is the world's first industrial robot created in 1962. The development for it started in 1954, but the first installation was in 1962 to General Motors as a pick and place robot and spot welding. So they did those two things with it. And after, of course, number 3 comes the number 4, Industry 4.0. So as things went on with the Industry 3.0 and the things it brought with it, they kept being developed. So robots were being fine-tuned, made bigger, better. Processes were being automated with different technologies. Sensors came around and stuff like that. But at some point, it's not enough that you make the robots faster or more precise. Sometimes they need something else. They need intelligence. So that's why there's the Industry 4.0. In Industry 4.0, which happened around 2011, we got these things that weren't as much as physical, but more virtual. We got things like IoT, machine learning, AI, cybersecurity, 3D printing, big data, and smart robotics. So big terms around that field. And quick recap on the big fours. So look back on the Industrial Revolution, or the evolution, how you want to say it. We saw the development from the use of mechanization of processes to mass production, then to automation, and then step further to digitalization. So what digitalization meant was bringing everything to digital form to use the data gain from the production of process or product itself to further develop it. Where does this all then bring us? Now that we live in the age of Industry 4.0, I'm not sure if Industry 5.0 is knocking on the corner, around the corner. It really is, at the moment, it really is all about digitalization and virtualization, big data, IoT, machine learning, and AI. And of course, digital twin too. But how can we use all these in our industrial progress or factories or processes? One way is okay. There was some weird noise coming from over there. One way is smart manufacturing. So let's think about more for what smart manufacturing really means. I mean, there are like many different definitions for it. This is one definition from Evgenov that says that smart manufacturing means using smart manufacturing processes like CNC machines or welding with industrial robots connected to their digital twins with real-time connection. The use of a digital twin has many advantages for controlling smart manufacturing. Digital twin can predict and analyze the processes in real time. When the twin is running in a simulation environment, it's constantly able to take advantage of the variety of expert knowledge produced as a joint effort of AI, IoT, cloud services, process control, and process. And this means that everything really becomes fully automatic. And this way mean, for example, that artificial intelligence and deep learning, if they are used in advance, this can solve challenges that are predicted to arise in the future that will be coming. So these systems can start to predict things to come. So, like mentioned just now, was the digital twin again. It's a head subject of this training, yeah. And it's an important player in the manufacturing field itself. In the image here, you see a rough digital twin model, or you would see a digital model, basically. This is not a digital twin, this is a digital model. But the digital twin itself is no way an easy subject to tackle on, as it's very multidimensional and it has so many aspects on it. It's not an easy thing to just start using and start taking advantage of. But the rough explanation of a digital twin is that it's like a digital copy of a physical existing process or a robot cell or a product or a factory. Like there's a huge variety what it can be. It can be a small thing or it can be a whole factory. Basically, we really can make a digital twin out of anything if we want to. But what is the use? And at what level we want to make that digital twin? That's one question. And is it really a digital twin if we just make it digital? If we see something and we just make a 3D model out of it? And can we say that that's a digital twin after that? Well, we will get to that later on. And we will now jump on the subject of twins themselves. First, we will check on the hype cycles for emerging technologies to see that digital twins are like still coming. They're really new, and how they will change the field, so to speak. And then we will check on the history of a digital twin, and then take a little glimpse on the different theories of a digital twin. The theories or concepts, so to say. That's why there's like different concepts and different theories, because it's still so new and there's really no standardization done on it just yet, because it's like so to say officially it's created in like 3 to 4 years ago. But we will get on that on the history path. So, hype cycle for emerging technologies. If we check on the charts done by Gartner, you can see that the digital twin is in the no, I'm missing one chart. Well, it's in the 2016 hype cycle for IoT. chart by Gartner, digital twin was like in the beginning of the innovation trigger phase. And if we now check on the chart done by them in 2017, we can see that it's rising near the peak. And it's getting noticed. It's starting to get noticed with all of these other things that are here, like quantum computing, 5G, 4D printing, smart workspace, and etc. So it has risen on the plateau, so to say. And if we go 1 year further, so 2018, we can see that it's almost at the peak. It has peaked, so to say. So there's like really a big expectation for it. And if we look at what the color of this ball means, that where it's placed on, it means that the plateau will be reached in 5 to 10 years. So digital twins will be big in like 2023 or 2030. And I mentioned 4D printing, for example, here on the 2007 chart. And if we check the 2018 chart, there's not much improvement, so to say. And if I remember correctly, in the hype cycle for emerging technologies 2019, digital twin wasn't on that chart anymore. It was replaced by a digital human twin, or some other words were used for that, but digital twin was not on that chart anymore then. But yeah, it's new player in the ballpark, so to say, and it still reached the hype peak so quickly. So about the history of this digital twin. I mentioned earlier that it was officially, so to say, created in 2017, 2018, but the roots for it are really earlier than that. It's partly new thing in the 2000s, but the rough concept for it. I mean, you have to talk about rough now, because we have to jump back to the 1960s or 1970s. So because then's the ideology for a twin in the industrial or use of a twin product came into use, because in 1970s NASA thought about it and came up with some type of a concept that they really used in 1970s. In that time, NASA applied the concept of its so-called digital twin into their Apollo 13 program. But what they did, of course, they didn't use a digital twin, because computers at that time weren't that good. But what they did was a physical exact copy of the whole system on the ground level to match all of the equipment and space, which meant that they basically had a space shuttle on the ground level, which had all the exact same panels and equipment and settings and the one that was at the space at the same time. Why did they do this? Well, it was because they could now run out different scenarios on the ground level before they would suggest any solutions to the team in space if the team in space had any problems. And if you remember know the history of Apollo 13 program, there was a little mishap with the flight. So Apollo 13 program really became one of the most famous rescue missions again. And the major role was with this rescue mission. It was this so-called digital twin, which in this case was the physical part on the ground level, because the engineering team couldn't straight out just suggest a solution to the team in space. I mean, of course they could, but it wouldn't be applicable to this case as the space shuttle had malfunctions or damages, and they didn't know exactly how it would affect. So they had to simulate those variables on the ground level. They had to choose a little adjustments or take some parts of the systems offline so they could simulate their ground level space shuttle as closely as possible with the one at space, and then test out different solution what you could do with it before they then send out their suggestion to the team in space. So this was really a major player on the rescue mission, and might be so that without this so-called twin, the rescue mission would have been such a success. So that was like basically an early concept which was tested with NASA at that time. They didn't name it a digital twin, but in a way they had the ideology of a digital twin in it. But then in 2002, in University of Michigan, Dr. Michael Greaves gave a presentation about Product Lifecycle Management Center. There was a slide in the presentation which looked like this. In the image, it shows two different spaces. It shows there's the real space, the physical world where we live in, where the process or the factory or the product itself exists. And then there's the virtual space where the product, process, or the factory's virtual twin exists. It's modeled as close to its counterpart as possible. So any variables that are available in the real space are taken into consideration in the virtual space. For example, efficiency of a process or throughput time for a process will be transferred also, obviously, into the virtual space. This concept idea did show that all of the elements of a modern digital twin, as it had the connection from the real space to the virtual space, delivering the data straight from the source. This meant that all of the sensor information from the real space or the real world application could be transferred into the virtual model or virtual space. So the data or the sensor data was sent on to the virtual space, and the virtual space talked back with information on the processes back to the real space. And then the virtual space model, you could drive the virtual space model with gained data from the real space and run it basically faster. So you could see into the future, so-called. You could test out that if we continue with these variables, where do we end up with? What's the end result? And in the image, you also see that there's like from the virtual space, there's still additional virtual spaces that you could run. In the conceptual idea, it was that you could run different variations of the virtual space idea. You could test out with different variables at the same time. So of course, under the testing out different scenarios with minor tweaks in the settings or the values gained from the data. So you could, for example, take one shot of data, so to say, and take that into the virtual space, then run first like one simulation with that on the virtual space 1, and then the second virtual space could be run with a little minor tweak to the same data, and see where that goes. And you will run these virtual spaces as many as possible at the same time. For example, some processes could, their speeds could be slowed or sped up, or parts could be developed earlier to a place where they will be needed, thus testing if this affects the speed of production. So first time when this concept was shown, it was really in 2002 or 2001, like it says in the description in the image. It was referred as a mirrored space model. And in 2011, the concept was then expanded widely into a bigger picture. It was still referred to as an information mirroring model, but the term digital twin was at that point connected to this concept as a way of describing this whole idea. And after the whole ideology has been called a digital twin, and the term has come somewhat into life. So it came into life in 2002, but in 2011, the name or the term digital twin came for this conceptual concept, so to say. And in 2017, 2018, it's really boomed, because then there came the different theories of a digital twin. There's quite many of them. Here's just a few, like four concepts or theories, so to say. So it's just not one concept or one theory of a digital twin. There's quite a few, in fact, and there's just a few. There's quite many more, and some companies like Siemens, Valmet, IBM, and Catmatic, they each have their own ideology on what a digital twin is. But they all still agree on a few things, that what makes a digital modeling, what makes a digital twin. There are some things that are common with each of these concepts, reasons with all of this, and we will get to them in the end of this section. But as you can see in this list, there's just a few. As you could say that there's always room of improvement, or for a concept, or just to take the same idea and brand it with your own, even though the goal or the main thing is in the end the same, to make a digital twin. There are just a few different ways to look at it. I mean, there's the original digital twin concept, that what we just talked about in the history. Then there's the NASA's digital twin concept, which is basically same as the original concept, but they have been targeting that concept more on the space shuttle and aerospace, aircrafts and stuff like that. And then there's the 5-dimensional digital twin concept that takes like one step further the original concept. And then there's the model-based digital twin concept, which focuses more on the management systems than the product or process itself. Again, like I explained earlier, the history part, this was created by Dr. Michael Greaves, and the idea was that there's 3 different parts. There's a physical space, digital or virtual space, and then there's the connections in between them. Data and information. Data goes from the real space into the virtual space, and the virtual space answers the real space with information about the process, or information and the process. And all the other theories or concepts are based upon this. So, because this was a rough concept, you could really go to any direction from here. And next was the NASA's digital twin theory. It was same as the first concept, but goes a little deeper and more specific on certain subject. It's not applicable to anything other than NASA's own things. In NASA's digital twin vision or concept, the digital twin is an integrated, multi-physics, multi-scale, probabilistic simulation of a vehicle or system that uses the best available physical models, sensor updates, fleet history, and all the data that is available concerning the physical vehicles or systems. This is done just to be able to mirror the life of its physical twin, which is NASA's case in space. So they use all the data that is available, even the history data. And the twin is described as an ultra-realistic one and may also include one or more important and interdependent vehicle systems, including their propulsion or energy storage, avionics, life supports, vehicle structure, thermal management, and etc. And in the addition to those, the physical models, the digital twin integrates the sensor data from the vehicle's onboard integrated vehicle health management system, its maintenance history, and all the available historical and fleet data obtained using data mining and text mining. So now came a few terms from the Industry 4.0, data mining and text mining. Those are AI things. So it's not only connected to the physical twin itself, but also all of the systems that NASA has, which saw the historical information of different situations. So it has access to those too. The digital twins systems that are on board are also capable to mitigate damage or degradation by recommending different changes in the mission profile to increase both the lifespan of the ship and the probability of the mission itself. So they have really thought about their digital twin concept really, really far. And in 2012, they took their vision into use, even though many of the components weren't still even available at that time. Many of the ideologies or technologies wasn't really just made yet. However, NASA made the decision still to move forward with these tests because they wanted to really start using their own digital twin. So they used all the best technologies available at that day, and to fill the gaps in the concept, they utilized US Air Force and NASA's own technology as best as they could. NASA took some part of F-15 fighter jet for testing to be able to proceed further and faster towards the realization of their vision of a digital twin. So they really wanted to push the ideology to become a reality as fast as possible because it will help so much with space flights. And next, it should say 5-dimensional. It says 5 parts. There's a little typo there. In the 5-dimensional digital twin concept created by Fei Tao and Meng Zhang in 2017, it's very similar to the original theory, but the 5-dimensional twin consists of a virtual and a physical version, their connections, data, and service. And as you can see in the model is seen as a 3-field model with a physical as well as a digital model at the edges. So here is the physical shop floor, and here is the virtual shop floor. And third one is the service up here. There's the ERP, PLM, and CRM, and MES. And data from each edge is then outputted to a digital twin model at the center, which in turn conveys the information and instruction back to the edge portions. So the physical shop floor pushes data to the digital twin, and the virtual shop floor also pushes data to the digital twin. And the digital twin in the middle of the model contains the data of the other parts. It has the predictive properties and forms of a digital part on the information it receives. The different parts of the model interact with each other and synchronize their data continually. So they talk to each other all the time and keep in touch, so to say. And the biggest difference is the service part of the model compared to the original model, which consists of different systems. There's the supply chain system, SCM, enterprise resource planning, ERP, product lifecycle management, PLM, customer relationship management, CRM, and plant design management system, PDMS. Although the model is very theoretical, the benefits of the model are problem prevention, quality improvement, anticipation, consideration of resources, and consistent quality of products. Another advantage of the theory model is that it considers the systems used in the digital twin and focuses on the parts between them, their interaction. So, as you can see, it's really, it looks basically simple, so that there's interaction between all of the systems on all of the floors, and there's data going through there, and it's mentioned as a straightforward and a clear model, but I have to say that it's really not. It's pretty complex in the end, like all of these theories. Then there's also the model-based digital twin. This is a digital twin that can be benefited as a machine learning environment. The concept is based on the integrated management systems on 1-to-1 scale. And the model-based digital twin allows the real industrial control equipment to take advantage of the simulation models, and this then enables the simulation of the models in real scenarios with real dynamic variables. Different tests and scenarios can be tested without adaptations by utilizing the digital twin, as the model in the digital twin stimulates the behavior of the digital control components. Again, really complex in the end if we start to get really deep on this. But basically, this is the same as the original model, but it focuses more on the digitalization of the management systems and their integration with concrete management systems, so that they can be simulated in the virtual environment as genuinely and accurately as possible. So it's with this theory or this concept, the focus is more on the management system. So like we saw in the service level in the 5-dimensional, so the ERP and MES. And as machine learning is heavily tied to this concept, the creators of this concept also mentioned that machine learning is really important requirement for a digital twin in the end, and specifically for this type of a digital twin concept. So theory's conclusion, or so to say, as you can immediately notice that the original theory is missing from this chart. Well, that's because it works as a base for all of the other theories. So it's not mentioned here at all. But when we compare these theories between each other, we can see that there are similarities in between and all the differences that they each provide. One of the major differences in this is that the NASA's model, as it's heavily focused on the simulation of aircrafts and space shuttles and problem anticipation. It's a lot more complex than any of the other models because it involves so much data. which it's a lot more complex than any of the other models, which in a way is really because of the complexity of flying and space environments. But things in common with all of this is that they all agree that there's a virtual space and a physical space, and the communication between those two spaces is really important, and it plays a major role, obviously. And also, I mean, the data going from the other and the other responding to that data is really important. So using sensors in all of these theories is crucial to get the valuable information out of the other space into the other. So hopping that data from the virtual to the real and from the real to the virtual. Also, they all use simulations and models of the processes to mimic the physical systems as close as possible. They all try to get some information for prediction and diminishing the risks in production or in the processes themselves. So they all work a bit differently, but still the same. If you catch what I try to say, they all work different, but still the same. But then we arrived at the topic, digital twin. Not everything is still a digital twin that could be explained, and it would fit all the criteria that was just mentioned in the theories. If something is said that it's a digital twin, it really may not be in the end, because I mentioned in the beginning that there's like different stages of a digital twin. That's because, no, I think we should take a break before I take the next slide, because it's going to be a long talk and we won't have to break at the appointed time. So maybe we start the break now and continue 5 past, like it was mentioned. It's 3 minutes early, but it will be better to get the break now than in like 15 minutes or 10 minutes. So let's take a quick break and let's carry on 5 past 4. 3 or 4. Yeah, let's continue in 10 minutes. All right. So let's carry on. So yeah, digital twin, not everything really is a true digital twin. Meaning that even though it's said that it's a digital twin, it isn't a real digital twin, according to the theories just mentioned. So what this means, that it means that there really are different levels or different stages of a digital twin. So now we talked about the theories about the digital twin, few of them. What makes it tick in the end? What's the theoretical explanation behind it? Now let's talk about them in practice. And first, before we do that, we need to establish the fact that there's really different stages of different level of digital twins. Stages also. Experts and company people will call their simulations digital twins when in fact they might not be one according to the theoretical explanations. I mean, it's not wrong, obviously, but there's a different name for it. Because digital twin ideology or technology is really new still, and there's so many understandings of it. I mean, different ways to look at it, different aspects, different ways to understand it. It needs to be categorized into different levels or stages, so to say. And because it's really not standardized just yet because of the age of the technology. But in the image, you see three different things. There's the digital model. That's the stage one. Or should we say, yeah, stage one. And then there's the digital shadow. That's the stage two. And then there's the digital twin itself. These are the three stages of a twin. These stages also show the development of the digital twin, as it all started as a digital model, then into a shadow, and then into a twin. I mean, the ideology. Even though the theories they all started from the stage three, so to say, but in practice, everything started with stage one and then developed into stage two, and now we're really on the stage three. On the verge of the stage three. Some companies or some companies or some companies and some analysts have crossed that line, so they have made real digital twins too. What's the difference between them? What do they mean? Well, the digital model is a digital representation of an existing or a planned physical object, product, or robot cell, or a production facility. There's no data exchange between these two objects. I mean, automatic data exchange between these. It's just a planned product, how they would exist in a planned product or just a digital copy of a physical one. But there's no communication that much. Yeah. These models are either just 3D models or just simulations of the plant factories. And if by any chance there could be any data implemented on the digital model, it will be inputted manually. So, for example, worksheets on Excel or order lists to test how the plant factory would work on that order. And in this model, the changes in the physical model or object, so to say, do not anyway affect the digital model and vice versa. So whatever we do with the digital object does not affect the physical object itself at all. and whatever we do to the physical object does not affect the digital object at all, unless we force the change ourselves. We force the change on them. So it's just a digital model of a physical object. We can change it as much as we want, but the change is in our hands, not with a machine learning system or AI or anything like that, because there's no active communication between these two. And what is, when we look at the stage 2, the digital shadow as a step forward into the digital twin. But if you look at it, you can see that there's only one way, one talk, so to say, of automated data exchange. So the digital model itself can output the data into the physical object, or vice versa. So the physical object can output the data to the digital model, but there is no feedback. If the digital model says hi to the physical object doesn't say hi back. He just left the digital object hanging. Unless we then again type the hi ourselves as a reply to the physical object. So what this means that any change is happening in the physical object happen in the digital object, but not the other way around. So any changes we do in the digital object don't happen in the physical object. So there's only one way communication. We will, and mostly, I mentioned briefly that I will show on the days 2 and 3 more on the practical things, so more on the simulations and so-called digital twins or digital shadows or digital models that we have done, and most of them are digital models and digital shadows. But if we take again one step forward, and when we talk about the true digital twin, we mean that the data flows between an existing physical object and digital object, and it's fully integrated to both directions. So now that if the digital object says hi to the physical object will say hi back. So again, any change that happens in the physical one will also be transmitted in the digital one. So they each follow each other. And in a real-time application, if we think about it, does this make any sense in a way? If we have a machine running and we have a digital model of it and we follow it real time, does having a digital twin just doing that make any sense? Well, in a way it doesn't, because we just see the same thing but in virtual space. But that's why we need to implement machine learning and AI and all the other data from all the other systems, and we need to start running it not real time anymore. We need to start running it faster than real time. So we will see that what these changes will do in the end. So where can it be used? This is just a small glimpse on where is it being researched on and implemented somehow. And I'll go through just a few of them. Obviously, manufacturing is there in the list as it's one of the most beneficial out of it. If we talk about, again, not maybe digital twins, but digital shadows and digital, if we talk about digital twins, but not in real time, but the ones that, again, predict the future and start running faster than real time. they use the so-called simulation time. Those ones are the most beneficial in the manufacturing sector. But yeah, will it really be beneficial to use the so-called real-time digital twin in manufacturing, or would a digital model or a digital shadow term to be used? That's the question we arrive once again in this aspect. But again, the importance that you can really test things out before you even have anything bought, or you can design an assembly line or a manufacturing process itself digitally and check what's the bottlenecks, and would it be even plausible to implement into the environment that you're planning to implement into. Most of our talking about that, most of our cases that we have done in simulation aspect and so-called digital twins or digital models are just this, that is it possible to create the process into the area that they have been thinking about doing it? Is it possible to make it work with equipment that they have thought that they would use? For example, certain robots, certain CNC machines, and etc. But we will go deeper into those in the other day. You could, for example, check in the digital model if really a certain robot could do the task that has been done manually earlier. You can like take the environment that is on your workshop floor and make it digital and test out. Is it possible to replace the human for other tasks from there with a robot? Even before you buy anything. And then there's the automotive industry, where it's also being used, as it's being used as a designing tool in it. First, designers take you will think about it as artistically like a clump of clay, where they start molding the car to look like their vision that they want it to look like. So they start molding the clay so it looks like the end product that they want it to look like. And then that is taken over to the other engineers, who then breathe their life into this vision, so-called. What this means that they start implementing all the components of the car. I mean, the designers just design the shape and the structural parts, and then the other engineers, the second team, so-called, start using this digital twin or digital shadow. Now, I think it's more called digital twin in this case, and they start wiring, for example. They start inserting all the components into the car, the motor, the electrical systems, all the mechanical parts that are not in the body of the car itself. And as each of these are added, the designers or the engineers can follow the development from the digital model or digital twin and see if there's any problems with the implementation, if they really can put the motor to that section, or do they have to move it a bit around, or is it possible to use the motor here, or will the belt be hitting some other components? So they can check everything before if there's any problems. There are like multiple softwares used in this process, and it's not one software can do anything from designing to wiring the whole car, or to kinematic design, or the aerodynamics testing for the car itself. But there are like software product families out there that has this like linear way of designing a car available. That there's like you start with one software, and once you finish that, you jump onto the other one with the product created in the first one, and it's really a smooth ride, so-called. Anyway, with the digital twin following the whole process, they can be rest assured that the car won't have any major flaws that will be overlooked in a normal design environment, and not with a concept like this. Because again, the system also, the software also checks for all the faults or the flaws. And designing is the next one. 3D modeling and simulation have been part of designing pretty much. When there's any designing being done, it has been done, simulation and what 3D modeling has been part of it for like many years now. Of course, earlier days you drew it on a piece of paper and started designing. You did the technical drawing from that and started thinking, but now there's really the software where you can implement this 3D modeling software, that you model the part or the component or the mechanical structure that you want. And then there's the simulation software that you can test that part out for the aerodynamics or for the stress testing or for the heat transfers or anything like that. Because today's simulation software really offer quite versatile options for feeding the information, and they can be, so to say, locked in with certain attributes. You can like create a simple object. Let's take a wild object like a shelf bracket. You can design a simple shelf bracket to hold a shelf, and then you design the holes for the bracket, that where you want to connect the shelf bracket into the wall. And then you design also a little notch where you want the shelf itself be implemented into this bracket. So it's a rough design for the shelf bracket. So there's two holes for drilling, screwing the bracket onto the wall, and then will be one hole or one notch where you will implement, for example, the shelf. And that is being done with a 3D modeling software, but that can be taken in the simulation part of the 3D modeling software, and you can lock in, so to say, some parts of this bracket. So you can say that these screw holes that you have modeled here can't be moved. They have to stay in the position that they have been placed into, and the place where the shelf will be has to stay the same, because the shelf itself can't be modified. The shelf's shape cannot be modified. It has to fit into this notch or this hole. So you can lock those attributes in, and then you can tell the software, the so-called simulation software, you can tell it that there will be 100 kilograms for example, 100 kilograms of pressure or static force on the notch or on the hole where the shelf will be. There will be 100 kilos force pushing down, and then you can tell the software that design this better for me, and then it will take into consideration all these things that you have told it. You have told it that the screw holes can't move; they have to be where they are, and the shelf position or the notch or the hole cannot move at all. That has to be where it's placed into. And there will be a static pressure of 100 kilos to this shelf position. So now the software will calculate the best possible shape for your brackets. So in the end, your bracket will look totally different than in the first time you designed it. I will next time, on the day 2, I will show one live example of this, what I mean. Maybe it's really better to really show it than just talk about it. But yeah, with these softwares you can really simulate really further away these things. And because the softwares are like so developed, they also obviously follow the laws of physics nowadays. as earlier times they may have not have done that, or they didn't do that so well. And you will see again examples of this in the day 2. Well, I can say that every time they followed the laws of physics badly, because it all depends on the software used. But anyway, the products and the simulation of the design models can be set as accurately as needed. The level of accuracy is really in the hands of the designer. You can make a rough sketch, or you can make it detailed as possible, even to the 100 microns level. And with the help of digital twins, the designers can then simulate or test out countless of different geometries, for example, for the product, for the shelf bracket, for example, and then take the best solution from there and implement that into the design. This way of designing of products is faster, because you can see many of the problems or difficulties a lot faster, because you can see the problems and difficulties even before the prototype is even materialized. Because earlier days you had to create the prototype to even notice the errors in your design, but now you can see it digitally even before you have even pushed the button on the CNC machine or even got the first food for your prototype. So that saves, again, time, and saving time means saving money. But there's also the utilities and products and healthcare and infrastructure and training. There's a good example on the training on the day 2. I will show a good example where it can be used. And here's one example too. Why isn't there any examples of manufacturing in this? In this is because it's really closed. There isn't much information available on that. There's always products or designs or training or etc. Manufacturing processes or their twins. Information is somehow hidden, or maybe I say that so that it helps with your assignment. But we will step on that. We will check on that, what I mean by that further in the slides. So who use it? For example, General Electric company, for example, was an early adopter for the digital twin technology. They have made now like 1.2 million different digital twins for their customers and their customers have like jet engines, wind farms, offshore oil rigs, power generation equipment, pumps, compressors, chillers, and more. Basically, this has made a big impact on the savings for those companies, basically through waste reduction and preemptive maintenance of the parts or the products that their customers have. And also General Electric has developed for the healthcare sector. So they create digital twins for their customers. So they have developed also for the healthcare sector the idea that they could create a sort of an IoT band-aid, and that will stream the heartbeat, the blood pressure, the respiration, and other information into the cloud, where software could analyze it and alert the doctors of any anomalies. This could mean we go one further. This could mean that the patient could be under surveillance 24/7. Okay, of course, the patient can be under surveillance with the normal means. Like you can see in the picture in the middle, there's these patches that measure the heartbeat and all the other information. But that means when the patient is on the bed, and it has to have the equipment that is shown in the painting or the ports right here, that has to be connected to the patches. But with the so-called IoT Band-Aid, you wouldn't need any of that. The Band-Aid itself would work. So there won't be any wires, so the patient could move around as much as possible. So basically they would create so-called digital twin of their patient. And one where it's highly used is Formula One. They're using them too. As the formulas are created in 3D, the design, like mentioned earlier, the automotive designing, that the designers start from clay and move on there. So are the formulas. And you will run different simulations very easily, different simulation models very easily. For example, to optimize the front wing of the formula. Did you know that the front wing in the formula, it has 8 parts? But that doesn't sound much. I mean, there's just 8 parts. But to make those 8 parts, you need 800 different components, which include like molds, jigs for assembly, and jigs for testing and performance optimization. And just one front wing, and you need 800 different components. So designing these parts designing these parts digital twin in mind, you can very easily get all the updated models of the components, because everything changes everything changes immediately in all of the 3D models. If you change the shape of the front wing, it changes all of the jigs and all of the molds to correspond to the change of the front wing that the designer has changed. Then there's like infrastructure. Even the city of Singapore has a digital twin of it, in which the city uses managing the city itself. It's basically at the moment used for simulations of emergency situations in different areas, for example, stadiums or shopping centers, just to create the most effective evacuation protocols. And this is just the beginning in their so-called vision, what they're trying to do. And still could be implemented into water supply system, power network, or traffic control, or anything like that, parking solutions, or civil engineering, or etc. But everything is still in the beginning with this test, and it's still in the evacuation protocol testing phase. So they haven't taken that further. And good place where digital twin is used is training, like mentioned earlier. Training for driving, for example, excavators. They can be done with simulators which are like 1-to-1 scale with the real ones. One case example is a company called Sleipner, who makes these transport carriers for excavators. But they also are involved with running the excavator business. The company, with their digital twin, the company can now train their users or their clients with these simulators that they have. And they don't have to take the working excavator off from the field, because they can put the client into the simulator, and the client will use that for training on how to use the excavator. What this means in practice is that it brings the downtime very close to zero with these excavators, because if you take the excavator obviously out of the field, it means that there's no work being done. It costs money again. They also mentioned that the Sleipnir also mentions that 80% of the training is done with the digital twin models in the simulators, and last 20% is done with the real excavator. So if we want to put this into numbers, they say that before these digital twins or simulators that they had, it took average of 3 days of training for this with these excavators, but now it takes it took 3 days on average with the real excavator. So it meant that the excavator was 3 days away from the field. So they lost, so to say, 3 days worth of profit. But now that they use a digital twin or simulator, the real excavator is only 1 day out of the field. So the excavator can now be 2 days more on the field. So it saves again money because it can do more work. It's not there's no downtime on the excavator, so to say. And there's plenty of other also, but it's still so new technology that there's just big players like Siemens and General Electric and Etteplan, for example, who are implementing them for their customers. But there are still thriving companies that are also starting to provide these services. So if you think about making your own digital twin or digital shadow or digital model out of your, for example, a robot cell, you will need a bunch of different softwares to create the environments. And you will need, obviously, the information too. So what you require for creating a digital twin, you require for the physical part, you obviously require the dimensions or the CAD drawings or the CAD drawings of the machines or the 3D models of the machines. And then you obviously need the CAD drawings of the space where your physical robot cell is. Then you need all of the sensor data, you need this CNC machine connected, you need the other CNC machine connected too, you need the robot to be connected, you need the conveyors and their motors to be connected, you need the sensors that are on the conveyors to be connected, you need the camera that is on top of here inspecting the wheels, you need that to be connected too, and the other conveyor, and this flip table which flips the tire. And you need all the materials that are in the play because they also play a role. And you need all the dynamics on the movements, how the machines work. And you need, obviously, the workflow information and bunch more. But those are like the rough basics that you can start your work on. You need a bunch of different softwares to create these environments. It doesn't stop to these softwares that are mentioned here, like 3D modeling software, simulation software, and software controlling the simulation, because sometimes the simulation controller, so-called, can be also inside the simulation software. And then you need some way to connect between the virtual and physical, either a device or a connection protocol. Device would be like a PLC. But it doesn't stop to these softwares. Then you need to start thinking about the connections between the softwares. How is the data linked to each other? What protocols to use for transmitting the data in between the real world and the digital world? And if you have any sensors or cameras, then it becomes even more complex on implementing that data into it. For example, if you would like to make a digital twin of the robotic cell, you will need I'm talking about this one here. You will need the robotic cell communicating, for example, with a PLC, which it already probably does. Then replicate your whole physical robot cell in a simulation software, for example, Visual Components, and then connect that PLC to the visual components. And it doesn't end there. Obviously, you will need to program all the connection between the signals that come from the PLC into the simulation model and get really precise drawings for the exact measurements for each and every machine that you have. I mean, implementing the signals, each and every signal that is in those CNC machines, that's a task, but sometimes you don't need all of the data that is in the machine. Sometimes just part of it is enough. It depends on how accurately you want to make your model again. But after all, again, if you will do that, all that, you will see that the simulation model would move in the same way that the real physical model moves. So you would have created, you wouldn't have created the digital twin, you would have created a digital shadow. At the moment, you really can't call it a digital twin, you would call it a shadow, as there's no information then again going from the virtual model into the physical model. To do that, you will need machine learning, then that brings things even more complex. Even doing this in a simple form to make it like a shadow is complex enough, but to implement machine learning into that, it's not, obviously I'm not saying that it's impossible. Of course it's not, because it's being done, but it's not an easy task, so to say. And then you have to think yourself that, do you benefit from that? If you create a digital twin model out of it, or is a shadow enough? Because you can still make changes in the virtual model and see if it still works with those changes. Obviously, it doesn't affect the physical model, but the data will still come from the physical model. And would it be still working with that, with those changes that you made in the virtual model? And if we check on then again, what are the softwares on how to do it so-called easily and in simple form in manufacturing? What about the software that you can really make your digital twin or digital shadow or digital model? For digital models, these aren't, I mean, the visual components isn't the right way to go. But for example, SolidWorks, Siemens NX or Autodesk, their softwares are good for that. So what about the software? Of course, there's like several different softwares and software packages that you can make a digital twin with. Each are of industrial process have their own softwares that are used to create a digital twin. Here's just two of those packages or softwares mentioned. The two are Visual Components and Siemens product family. Siemens has like huge variety of software included in their catalog. I mean, in their catalog of softwares, as they have softwares from CAD to different stages of simulation softwares. There's simulation softwares that you can simulate a simple process in a robot cell, but there's then another software that you can simulate a whole factory with. And then there's yet again one simulation software that you can simulate your product chain with it. And they have the CAD, and the CAD is fully integrated with all of the softwares. For example, if you create a CAD file into Annex software, it can be easily transferred to the work cell simulation software. And when that work cell simulation is done, you can save that and then transfer that to the plant simulation software. So there's like steps that you can do easily because the softwares are so integrated with each other. It goes even so far that each and every component of the work cell simulation can be checked and monitored during the simulations. Then again, there's again, you guessed it, a software of that too. So they have taken this manufacturing or designing aspect to a whole new level with their softwares. And as we're talking about Siemens, they have software, but I guess they will be more known about their physical products, like PLCs and motors and controllers and stuff like that. And if they do software and do hardware, it will basically mean that those are two also integrated. So they have full integration with their physical products too. So you can simulate their PLCs in the software and then just implement that into a real world PLC. Not sure if it's possible yet, but it will be really cool to just make their simulation with their plant simulation software or the process simulation software as accurate as possible, add all the products and the components you would use in the production line, and then it will create the PLC code like automatically through that simulation, and you could just upload that into a real world PLC. No PLC programming required, as the simulation software could itself generate the code. My experience with Siemens software package isn't that so to say much. I have some experience on it, done some simulations on it, but I haven't that much experience with it. I have more experience with the visual component software. So I just thought that it will be a cool idea or a great idea if it will be. I guess it might be still in the future coming that they are thinking about doing that implementation. It will require a lot of AI in the background to realize all the connections between the components. But the other software, then there's the visual components, which only provides the simulation software itself. The software itself is quite visual, so it's a 3D simulation software compared to the traditional 2D ones, because usually the simulation softwares that you see are 2D, because you wouldn't, so on many cases or most cases, you wouldn't need visual simulation at all. But when you want to simulate like processes and with robots, you need visual simulation because you need to see and look if the robot really can reach and has the maneuverability to move inside, for example, a CNC machine, and what will be the what will be the movement path for the robot to go inside that CNC, for example, to grab a part or etc. The software is really usable for many things. You would like simulate a simple robot cell with it, or a simple pick and place task for a human being. You can simulate a whole factory with it. So it's very versatile in that way. You can do small things and big things with it too. One downside is that if you start doing big simulations, and as it's a visual simulation software, it will get really heavy, which means that it won't run that smoothly when we're talking about big factories. So if you want to run like simulations of a simulation time of like 8 to 16 hours, that will take, depending on the simulation size, but that will take like even 20 minutes of real time to run that simulation. But what that means that it will calculate each and every step, for example, a human takes, and take that into consideration, and all the movement paths for the robot and stuff like that. So that's why it's really, really heavy. As this is a solo simulation software, there's no other softwares with this company's software, and they have, by the way, they have named their product quite interestingly, because their company name is Visual Components and their product is Visual Components Premium or Essentials or stuff like that, but they haven't distinguished their product name. But yeah, they are solo flyers, so to say. There's no PLC or anything in it. There's no logic, but there's Python programming language implemented into the software. And pretty much anything that you can do with Python, you can do it in Visual Components too. All the plugins and all the snippets and all the gadgets that you love and use in Python, you can implement into the Visual Components itself too. And like I did say that there's no second. I did say that there's no PLC, but there's add-ons available for the PLC connection. There's like OPC, UA, and ADS for backoff. So you can add or connect a real-life PLC to the software, or you can add a simulated PLC too. So you will run a physical process through the simulation, or a physical PLC runs the virtual simulation. Either way goes. So it has the possibility for a digital twin. We will take, on the other days, we will take a look on how to make a digital model and maybe a digital shadow on this training. And there will be showcase of different cases in which digital twin, or should I say digital shadow or model, have been made. As really the digital twins are still coming technology. It's really new at the moment, and it's not standardized anyway at all. So there isn't any much cases for me to show on that we have done, but the digital twins and digital shadows and the digital models really do show a good image how this technology could be implemented into those. I mean, yeah, how you could implement digital twins into those cases or scenarios that I will show. But yeah, that was pretty much of that. The theory part, the big blabbering of the digital twins and their history, so to say. Here is it is a quick change of subject. Here is the first assignment that will be for tomorrow. I'm not really sure how I can I? Yeah. So here is the, here is the first assignment. And maybe this is partly the reason that I didn't show that much of the digital twins in manufacturing. That should read, by the way, in you. Yeah, no. Now I'm blubbering. I meant, yeah. The assignment 1 for tomorrow is to go on the internet and search for a digital twin in use, and then explain it or showcase it in a few sentences and link to the source. Maybe at a detail, do you think it's a digital model, a digital shadow, or do you think it's a real digital twin? Maybe add that to there too. And then comment 2 other posts that are on the Padlet. I will be putting that link into the chat. I have some issues on how to do that now because I can't seem to. Oh, no, it's wrong. Now it opens. I will be adding this to the chat. There we go. And yeah, comment 2 other posts. What do you think about them? And do you see them as a digital twin or digital shadow too? Yeah. not much to say about that. Pretty straightforward, I guess. Yeah, thank you. And that was a mouthful, so to say. Any questions about the subject at hand? Okay. Thank you. All right. Hope you got a little bit glimpse on what the digital twin is and understood it a little bit more or better. And yeah, really next time on Wednesday, we will be going through some simulation cases, real examples that have been done using a visual component software. All right. Well, if there's no questions, I guess it's just to say thank you all for listening, and you have a great evening for all rest of the day. Stop recording.